5.6 is on applications of integration, definite integral type stuff. So we want to look at the area of a region between two curves. So that's the next concept we want to check out. So let's suppose we had these two curves. Look something like this. We'll do this in a generic way. So you have an upper curve and a lower curve. So it could be something like this. Okay, we'll call that curve g of x. And then you have another one, like something like this. And we'll call that curve f of x, like that. Suppose you want to find the area between the curves from A to B, like that. So really it's this area here to here. So this region is what we're trying to find the area of here. So we need to think in terms of integration and a Riemann sum. So what you do is we're going to look at these representative rectangles inside this area like this. I'm going to actually try to move that a little closer like that. And zoom in a little bit. So these are what we're adding up. So if we're going to add those up from A to B, that'll be your limits of integration. You want to find the height of this thing, and then this is a delta x, or dx is the width. So this is my region. We'll call this my region R. And the height is the difference of the function values. So wherever you're at, say here. So if this is, we'll just call it x sub I. Then that we'll call it, so let's just say h. So h is the height of that thing. That's going to be f of x sub I minus g of x sub I. That ends up being like the height of that thing. and then we want to add those up. We want to basically say that the sum of that is the area between the two. So what you do is you partition AB. So this is kind of a setup concept that you'll see through the rest of calc. When you define these formulas and stuff. So you partition AB. And so your partition delta is A equals x naught, less than x1, less than etc., all the way to x sub n, which equals B. So you're partitioning this thing up, just like normal. You choose your C sub k in the kth interval, just like the Riemann sum does. Like that. Then your delta A, or the little area k, is going to be the height times the width, right? Or width times height, whatever you want to call that. So inside each one of those, your height is that difference we just calculated. So it's f of c sub k minus g of c sub k delta x sub k. So this is your h sub k. So that's, we'll call that I, whatever, either way. So h and then your delta x sub k gives you that area. So area of R, A, is approximately the sum of all the delta A sub k's, which is the sum over all the k's of f of c sub k minus g of c sub k delta x sub k. So height times width. And then you take the norm of the partition approaching 0, and you get the actual area. So the definition is all of that above, but we have to define f and stuff. So if f and g are continuous on the closed interval from a to b, and f of x is greater than g of x, and that's how I drew it. I mean, it doesn't work for this other side when it flips. Then you'd have to flip the difference if you come on this side, because this was my g, right? And then you just flip otherwise you get a negative value. So if f of x is greater than g of x for all x in AB, then area is equal to the limit as the norm of the partition approaches 0 of that sum, of the sum over all the k's of f of c sub k minus g of c sub k delta x sub k. And then that is the Riemann sum, which is defined to be the definite integral from a to b of that difference, f of x minus g of x dx. So that's how you end up going through and doing a derivation of these formulas you're going to get. Now, you don't want to picture it as just a formula, but you're going to see other concepts like this throughout the book, or any calc book, where you set it up in this way, and you end up defining this Riemann sum and taking a limit, and then it ends up being a formula in terms of your functions and an integration. Okay, so let's see, did I miss something in there? Not really. I didn't show you. So this is your delta x. So I said I here, we can leave it I there. And then you're picking some value, your c in here, c sub I. I think that's good enough. Okay, just a couple things on my picture, but we're fine there. Okay, so let's look at an example of this. So find the area of the region enclosed by y equal to 2 minus x squared and y equal to negative x. So it's enclosed by both of those, so it doesn't give you endpoints. We will have to find those out. So the first thing you want to do is sketch the region. Always got to sketch the region. So sketch the region R. And then we're going to find, I guess this is 2, find AB. So you want to find where they intersect. So let's go ahead and sketch those regions, or that region. And I kind of know what it looks like, and I've the picture down here. So you have 2 minus x squared, so you're up 2. Let's see, I went ahead and did it into scale. So 1, 2, and then you're over 1, down 1, over 1, 2, down 1, 2, 3, 4. So it's going to intersect down here. So this is 1, this is 2. And then you're over 1, down 1. Just going to go through that point. and then over 1, 2, down 1, 2, 3, 4. Just going to go through that point. So your parabola then looks like this. And then it would keep going, of course. And then your y equals negative x is going to be basically this line. Like that. Because we know it's on a diagonal. So we want to find these points here, which you can pretty much just count off because it's a nice graph. So that's 2. This would be -1. Yeah, so that looks good. And you can solve for it. So this happened to work out real nice. But basically, if you don't know how those intersect, you set f of x equal to g of x and solve for intersection. So let's just do that and make sure we're kind of verifying now. Make sure you get the right thing. Negative x and then 2 minus x squared. Bet that factors real nicely. X squared minus x minus 2 equal to 0. And then we factor it. Equal to 0. So x minus 2, x plus 1, and you can see 2 and -1. It's exactly what we thought. So your interval from A to B is going to be -1 to 2. So think in terms of the rectangle, the representative rectangle you're adding up. It's in here. It's this thing right here. This is your representative rectangle. You're adding those up from left to right. The height is the difference between the top function and the bottom function. So this top function is your 2 minus x squared, and your bottom function here is your -x. So it's the difference of those two that gives you the height of this representative rectangle here. Okay, so that's what we're looking for. And then you add those up from -1 to 2. From -1 to 2. The thickness is your delta x. Okay, so that's your thickness. And then you multiply times the height, h. So area, in this case, is the integral from -1 to 2 of 2 minus x squared minus -x dx. Okay, and so that's where I want you to work that out. See if you can get a good result there. And you'll check it later. Should get 9/2. Okay, is that making sense of what to do? And I want to fill this in so you can see the area. So this is the area you're looking for. That's your region. That's R. All right, let's do another one. Okay, next example. So find the area of the region enclosed by y equals x squared, x plus y equal to 2, and y equals 0. That's the x-axis. So this one is important to sketch it and see what it's really asking for first. So let's sketch this thing. Sorry, I was trying to get this thing the right size. There we go. And let's see what we got. So we sketch this. And we'll go 1, 2. So it's just a parabola, and then this is basically y equal to negative x plus 2. 1, 2. And so we have a parabola that's going to be like this. It's going to take off like that. And then, so that's 2, and then it would be up 1, 2, 3, 4. So it's going to hit up there. And then my other graph is up to a slope of -1. So it's going to go through those points there, like that. And so what is the region in question here? What are we looking for? So here's my y equals x squared. And then this is my, oops, didn't mean to put that there. This is my y equals negative x plus 2. So the region, this probably comes down like this more. All right, so it's going to intersect here. That's a 1, and this is a 1. Is between here. So this is our region. So we're looking at, oops, I was just going to make this something I can draw on better. We're looking at this region. So it's enclosed by those and the x-axis. So that's what we're looking for. So so you got a picture of the rectangle. Let's leave it like that for a second. The rectangle in there, how would you add that up? Well, you have this one as the top and then the x-axis. And then this one, the top and the x-axis. So you actually end up here with 2 different regions. So in this case, we have to break this up into 2 different regions. So this is R1 and R2. And in here, we're going to put in our representative rectangles. So this goes up to here and here. So there's my rectangle. And here to here, this is my rectangle. And they're different. The heights are going to be different as you go across from here to here. So we do go from A to B. So we go A to B. So A is 0, B is 2. But the area is the area of the 2 different things, 2 different regions. So area, in this case, you have to separate it. So area is equal to area 1 plus area 2, which are different. So try to set that up. What's that going to look like? Give you a second. So you have the integral from 0 to 1, right? And then it's basically, it's just a function value. You don't have to say minus 0. So the top one in this case is x squared dx. That's area 1. Plus area 2 is the integral from 1 to 2 of the negative x plus 2 dx. So that's what you end up getting for those 2 separate areas. Okay, so calculate that on your own, and you should get 5/6 when you sum them both up. It's 1/3, ends up being 1/3 plus 1/2. Now, there's another way to do this, and I think I'll separate that out. We'll do one more video on those. So think about another way to do this where you have one integral. How do you integrate this with just one integral? And the hint is basically you go across. So we're going to go this way and change in terms of, instead of having dx, we're going to have dy. So this is a dx and a dx, or delta x. We want to go this way and have our delta y. So we're going to flip the limits and have a function in terms of y instead of in terms of x.